This is section 3, DFT of signal systems and transform for Fourier transform. In this lecture, we'll discuss DFT from linear algebra perspective. We'll show that DFT is an orthogonal decomposition, and we'll analyze the analysis and synthesis equation of the DFT in matrix vector product form. First, let's revise what is orthogonal decomposition. I assume that you have some idea of linear algebra, and we are here just to revise orthogonal decomposition in one slide. What is orthogonal decomposition? Well, let's begin with this notation. We have a vector space Rn. Y consists of y1 until yn, and it is a real vector with n elements. It can be decomposed, that means it will be represented alternatively by a linear combination of u1 to up, and u1 to up is an orthogonal basis. So what is u1 to up? u1 is also u11, u12 until u1 n, which is also an n element in this example. u2, it is u21, u22 until u2n, which is also Rn. So u1 and u2s are also vectors of Rn. And basis means that linear combinations of u1 and u2 up to up will span the space W. What does orthogonal means? It means u1 dot u1 is equals to 1, or is equals to 1, and u1 dot u2 equals to 0, and the dot stands for the inner product or the dot product. Now, why is this important? Well, when we have an orthogonal basis, we basically can decompose y into this representation, and therefore now C1, C2 up to Cp will allow us to represent the original y as a linear combination of these bases, and we can now interpret y in terms of C1, C2 and Cp's. And because they are orthogonal, it is very easy to find what is Cj. This is the cool idea of Fourier transform. In the Fourier transform, the Fourier basis is the complex exponential, and the difference now is that the Fourier basis is not Rn, it is Cn, and in fact the input y don't need to be Rn, it can also be Cn, but if we have given it as only real numbers, basically it is still a subset of Cn, it's just that all the imaginary terms are 0. So when we view Fourier transform as an orthogonal decomposition, then we are actually saying that we are letting the input be real, but we are decomposing the real input into sum of complex exponential, and this complex exponential u1 to up are the Fourier basis, and the C1 to Cp are the Fourier coefficient. Okay, so in the next slide, we'll continue this discussion.